Right, so I've started the recording and all right, so okay, so we are running 5 minutes late for the today's session. No worries. And okay, so before we start, do you have any questions, follow-up questions from yesterday? Okay, so Abhishek, probably you tried to solve the quiz and you saw job and task trackers. So no worries, today we will cover most of it. Okay. All right, so good, good. That means you have tried to finish the quiz. Has anybody else tried to finish the quiz? Great, 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 great. So, all right. So, one thing which we have started doing it for last two sessions that we do a reintroduction because yesterday there were too many candidates and so today we can basically unmute you for maybe say 30 seconds or a minute and then you give your introduction and then we at least get to know each other because we are going to be in this class for next maybe 11 or 12 classes, all right, which is maybe 1.5 months. Okay, 5.5 weeks basically. So I would so is that okay with you? So I'll start from Abhishek and to till Vikas and one by one. So Abhishek, please unmute yourself and introduce yourself. Do you have a mic? Sorry. So can you unmute again because there's a lot of noise coming in. All right? Yeah, but there's a lot of noise. Yeah. There's a lot of noise coming in. Yeah, please introduce yourself, huh? Okay. Okay, great. Great. So Abhishek is probably the youngest of the group and all right. So uh, Amish, would you like to introduce yourself? Okay. So Anirudh, would you like to? Amish, would you like to introduce yourself, or should we move on to Anirudh? No, I don't hear. So you have to unmute yourself. There is a button to unmute yourself, and then you can speak. Okay? Yeah, yeah. Okay. Okay. Great. Great, Anirudh. Great. So, all right. All right. So you can mute. So Amish, we were not able to hear you. Maybe there's something wrong with the mic. So maybe yeah, we can go ahead with Aruna. Once you have the mic ready, then we can have your introduction. So Aruna, would you like to introduce yourself? Yeah, yeah, we are able to hear you. Mm-hmm. Great, great. Thank you, Aruna. Nice to know you. Dia, would you like to introduce yourself? Yes, we hear you. Great, great to know you, and Dia. And all right, all right. Thank you, thank you. And Kirti, would you like to introduce yourself? Mm-hmm. Great, great, great. Thank you, Kirti. Lingli, would you like to introduce yourself? Great, 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 great. Nitin, would you like to introduce yourself? Yeah. Great, great, Nitin. All right. So who is next? So, so, so it's once and then. Yeah, yeah. We can hear you. Could you be a little louder? Yeah. Okay. Mm-hmm. Great, 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 Ingoba. Yeah. And so, Prem, would you like to introduce yourself? Okay, 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 okay. Great, great. Thank you. Thank you, Basant. All right. So, Robert, would you like to introduce? Great, great, great. And yeah, so great, great to know you, Robert. And all right, Seth. Yes, we can hear you all. Great, great, great. You are in a very interesting domain, and big data is definitely going to help you. And Sandhya? Yes, we can hear you. Yeah. Great, 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 great. Thank you, Sandhya. Thank you. All right, Srinivas, would you like to introduce? All right, so we move to Vikas. Srinivas, once you are ready, let us know. Vikas, would you like to introduce yourself? Yes, great, 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 Vikas. Staying connected, and if you have, guys have any doubt, so there are two more people who want to be introduced. One is Abhishek Verma. You can go ahead, Abhishek. Great. Yes. Come again, please. Could you come again, please? I could not hear. Uh, yes, yes. Go ahead. Okay. Okay. Great. 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 Welcome, Abhishek, and you're going to definitely find this course useful. And do you want to introduce yourself, Amish, now? Yes. Great. So, all right. So we have a very great set of team here, and I'm sure I'll be able to do justice to the course, and I'll try my best to basically meet your expectation. If there are questions or any doubts, feel free to drop me a personal email or drop us an email at hadoop at no big data, or feel free to give me a call. And so that's about something if the course is not meeting your expectation or there is some other problem you have. And for with respect to the topics which we discussed. Okay, okay. So yes, you can go ahead now. Ingoba, did you? So all right. So please go ahead. What? Yes, please go ahead. Okay, okay, okay. Please go ahead. Okay, okay. So we have one more person to introduce. Please go ahead. Okay. Okay, brilliant, brilliant. So, all right, welcome, Sean, and I'm sure you will be benefited from this session, and I'll try my best. All right, so I think we have only missed Srinivas. Other than that, everybody has finished the introduction. All right, so let's get started now, and so. Vikas's point was, can we discuss quiz questions today? So there are because there are few things, few topics which are included in quiz, which are not which have not been discussed yet. So I would like to finish those topics, and then I would like you to go through it again, and then we can have the discussion on the next session. All right. So the reason is that earlier our first session used to have everything HDFS and all those things, but then we realized that it did not give much time for the question answers. So we have moved some of the topics to the second session. All right, and that is the reason why the whole course has become 12 sessions instead of 11 sessions. Okay, so it might be a little come to you as a little surprise that we planned for 11 sessions, but the course may go on for 12 sessions because of multiple reasons. First, we had to increase the size of our course on Zookeeper and Spark. We had to go into more details because apparently those two topics were most beneficial to most of the people. Okay, so we had to increase the size of the course. Along with that, we have introduced yarn, and because of this, the course has become little bigger. So instead of 11, it is going to be for 12. Okay, so I hope you do not have a problem with that. Okay. And also this will give more bandwidth for all of us to have a little more healthier discussion. All right. Okay, great, 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 great. All right. So again, our mode of discussion would be that all of us will have to, keep on typing, and because otherwise there'll be a lot of yeah. But you can tell me if you want to unmute, then you can just type in the chat window and then unmute yourself. All right. Okay, because in the video call the voice collision happens quite often. All right. So okay. So again, a quick recap. Yesterday we talked about HDFS architecture. Other than our basics of big data, in our discussion earlier, what we have done is we have emphasized on the point that big data technologies are all about distributed computing, and The various architectures would be actually covered throughout the session. These around 13-14 components which we are going to cover will give you a full 360-degree view of the various architectures in the distributed computing or in the big data world. Alright, so that was the first point of discussion, and we also discussed the bigger the data, the better the results, for example, recommendations and others. And the other thing which we emphasized was that it's not only the processor, these are other components as well. And single computer doesn't really solve the problem. And so afterwards we discussed something called HDFS. It has basically Hadoop distributed file system. It has name node and data nodes, and name node keep the metadata, data nodes keep the actual data. So alright, so then we have an HDFS blocks uh, where each file is broken down into blocks and it's kept somewhere. So we'll give a demo of these parts so that you understand it. So each file is broken down into blocks of each of 128 MB. Earlier it used to be 64 MB. Now it's alright. Okay, thank you, Lingley. And alright, but this additional session might come a little surprise to those who had planned for other things. Anyway, so we have a file broken down into 128 MB pieces, and these pieces are replicated across the multiple machines, so that in case one machine goes down, these pieces are again replicated in order to bring the total number of copies to 3. Okay, and also this replication factor of 3 is completely up to your configuration, and we can change that. Alright, now the other thing which we need to understand is that the architecture, the data does not keep on coming through the name node all the time. All we need to do is all the client driver, which is the command line or the software layer which we will use, this software layer will go to name node first and then find the location of the blocks for the file you are trying to retrieve, and then go talk to data node directly and retrieve the block and give it to you. Okay, so that's a model. And now again, the name node metadata is basically what? The number of files, the list of files, the folder structure, folder names, and what are the blocks of each files, and how many replications are there for each file, and so on. Okay, so those are the number of blocks of those are the metadata which is stored by name node in the memory. Okay, and when we are making the changes to a file, creating a file or deleting a file, that is a transaction. That's a transaction log which name node need to maintain in order to have in case there is sudden crashes, so there is a way of recovery. Okay, so this information is persisted into the file system only, the transaction log, while metadata is kept in only in memory as well as saved onto the disk. All right, so that's a brief recap of what we have discussed so far. And okay, so here you can have a look at alright, so yesterday we also discussed few more things. One was our HDFS overview. So were you able to log into any of the clusters so far? So this one will be easier for you. You can simply go to hadoop1.nobigdata.com at this particular port. This login and password is given in the installation document provided in your account. Alright, if you log in into your account, you go to No Big Data and My Courses. Under that, when you, I have so many courses because of the history, but not this one. Yours is 30 May. All right. So this one, if you look at it, there is an installation instruction. All right. There is installation instruction, and you can open it, and there'll be password in it, and there'll be so you generally do not need to install the virtual machine on your on your computer. All you need to do is connect to our server. If you are on Windows, you can use PuTTY. If you are on Linux or you are on Mac, then you can go to terminal and simply say Hadoop, sorry, SSH, Hadoop 1 or 2 or 3 or 4, Hadoop 1. Right now I'm saying Hadoop 1, nobigdata.com. Also, before this, you can put student at nobigdata at Hadoop 1. All right. Thank you. Thank you, San. All right. So now you can see that. So it shows that the last login of this account. Now, from here also I can talk to my file system using Hadoop FS. We'll discuss in detail a little bit more. And from here also we can go to the file browser and have a look at the files. Okay, so this interface is called Hue, and it gives us the ability to talk to Hive, Pig, and HDFS and Uzi. So those kind of components we can control through the browser as well as from the command line. All right. Now that's about the file browser here. Now let's take a case of this particular file. Okay. So when you are also, please all of you note that if you are fiddling around here, so please create your own folder. Okay. So uh, is everybody else able to hear me, or is only Anirudh who is not able to hear me? Okay, so everybody else can hear Anirudh. So you might give it a little more try. All right. So here you create your own folder before 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 putting any file, the way other students have put in, you also put your folder. Right now we have not created separate account. Reason being, this one gives a little more open environment for when I'm doing something and you try to log in from your own account and then you see that those files are not there, that becomes a lot of inconvenience. We always had earlier we started with individual accounts, but then it became a little more hassle to keep transferring files from one place to another, and that's when we basically stopped uh, you know uh, having separate accounts. All right. So you can see that there is, let's say that there is this file called betting.csv, and in this is the folder. Okay, so same thing, we can, let's have a look at the blocks of this file. Okay, let's say what was that file name, betting.csv. Okay, so we'll just see what are the blocks for this file. Okay, so this file betting.csv is, it's showing you the details. Do not get intimidated by the text, just try to understand it. So it shows that connecting to name node, and this is the name node location, which means our Hadoop one. If it says file system check started by the student using a simple authentication, and here it shows you that these are the blocks of the file. You see, replication factor equals to 3, and these are the different machines containing the blocks copy. Okay, first one is this IP address. You see the IP address from here to here. Okay, all of these four IP addresses are kept on the same rack for time being. Do not worry about the rack right now. Just see that there are three different machines containing the blocks of the data. Okay, and these machines basically keep the data in a local folder. It is under cd slash var slash hdfs, and under there you will see the block files. Okay, and we can change this number of blocks from 3 to more than 3, and I think there are more than 3. 1, okay, 2, 3, yeah, it's only 3. Okay, and it says that so it shows you the full status. In case you shut down one of these machines, it will start replicating this data to another machine. Okay, you can see that. All right, and total number of data nodes are 4 and number of racks are 1. All right, so probably this gives you an idea that although on the surface this file looks nice, like a usual file, but beneath the hood it's stored on multiple machines and in parts. Okay, so right now, since this file is fairly small, 6.1 MB, therefore the data will be only single block. I don't have one file which is bigger than 128 MB. If I could, demonstrate to you. All right. So that was a little overview of these tools. So this is one way you can create your own folder here and then start working. All right. So now that was a very quick demo of HDFS. Also, if you want to interact with HDFS, you can start using Hadoop fs command, go through the help, and then you will understand. All right. And the other thing is, all of you, please send an email to hadoop at nobigdata.com with 3 slots so that we can have a one-on-one hands-on scheduled with you. All right. Although you may not require basically an overview on setting up putty and other things if you are facing a little challenge in connecting. So please, okay. So please send an email to Hadoop at nobigdata. So if basically you want a help on how to connect to the cluster and how to create a file in HDFS. So if you want a hands-on session, a one-on-one session, then drop an email with 30 minutes time slots, 3 different 30 minutes time slot, and then we will schedule a discussion with. Okay. So whatever time suits you, just give us 3 different time slots. Okay, preferably in some time zone which works for India as well, either morning or the evening of Indian. All right. Now let's start with the second component which we have discussed so far, but I mean at very superficial level. Yes, please. Yeah, anytime in the weekdays, and preferably evening or the morning of Indian time, or during the day anytime. So but you give your time slots, we will plan accordingly. Okay, so 3 different time slots, 30 minutes each. Okay, all right, so let's continue with our discussion the way. So after HDFS, that was a overview of HDFS, and let's talk about yarn. and that's a compute engine. So rather than jumping directly to yarn, we will first talk about, in a very simplistic terms, the way Hadoop 1.0 was. Okay, so the compute engine that we talk about is, let's start with a very simple problem. So you have got a simple computer, 1 gigahertz processor. It has you have got 1 terabyte data, and this 1 terabyte data has basically 10 billion names, 10 billion strings, each of 100 character length. Okay, so 10 billion names of 100 characters each, and the RAM in your computer is 2 GB. How fast can your computer sort this data? Sort means ordering the data in increasing or decreasing fashion. Okay, so if I'm not asking the approach, I am asking approximately how much time would it take? Okay, so Nitin says 5 hours and Sean says 5 hours. Who else? So generally it takes around 5 to 10 hours. Okay, depending on various aspects like how much hard disk you have got, and all right. So all right. So it basically takes around 5 to 10 hours. Okay, if you really have a great hard disk which is pretty fast, then it might go up to 3 hours. Basically, reading the data from hard disk will itself take 3 hours, and rest time will go into sorting the data, and you might have to rewrite the data again and again into the disk. All right. So there is Seth, there is no straight away way of computing it. Our traditional techniques in the computation were good if the data is all in memory. Okay, those techniques which we studied in computer science to compute the time, to compute the complexity, those techniques are no longer valid when your data is in the disk, because most of the time goes into reading the data. And the reason why this time, overall time, is equivalent to reading the data is because while the data was being read, parallelly the sorting was happening. So there is no extra time devoted to sorting, because while the data was being read from the disk, the sorting would complete. Okay, so and that is why the processor is taking about this much of time. Okay, so there is no straight away computation. The reason why I asked this question is not to check your computing background, just to check your hunch, just to check your instinct that uh, how what does it mean by 1 terabyte data to you. All right, because in other words, I will ask you this. So if you have 10 billion records in your table, in your database table, if you have 10 billion records and you want to create an index on this 10 billion records, how much time will it take to create an index on this 10 billion records table? Okay, it will be more than 6 to 10 hours. All right, because creating index means sorting this data. All right, so what's wrong with this? What's wrong with this? We might require faster sorting. So 1 terabyte is good, but the moment we go to 2 terabytes, the total number of hours might go far beyond twice. Okay, and we might have to we might need to sort bigger data, and we might need a faster response time than 6 to 10 hours, or we might have to do it more often, and therefore this is unacceptable. the 6 to 10 hours is not acceptable in the normal life of churning the data. And that is why uh, and you can see that the sorting problem what we have just discussed basically is the backbone of most of the computing. Almost most of the problems can be converted into sorting problems, and we will see that. And almost every problem can be aided by sorting algorithms. Okay, be it finding a path from one location to another, be it uh, grouping the users together, be it DNA matching. Almost every problem can be aided to a very large extent using a sorting algorithm. Alright? Now, similarly, a sorting algorithm, if you look at sorting, is the backbone of probably the whole SQL. Let's look at what does it mean by sorting in a traditional sense. So, if you have SQL, if you have an select query going on your database, it's basically if the data is not sorted and there is no the where clause, the data is not indexed on the where clause statement, the column on which we are applying the filter, if there is no index on the table, is going to take a lot of time. But the moment you create an index on a table, it basically makes it very faster. And that means that indexing is the very important aspect of the select query. And what is indexing? Indexing is sorting the data, right? The way we create index on the book, you have a book, we create an index means we take all the words from the book, sort them, and mark them at the end of the book that these are the words found at these locations in the book. Alright? So select query or where clause is simply nothing but a sorting problem. Similarly, grouping is of course a sorting problem. The moment we try to group on basis of a column, all it does is sort the data, and then after you have sorted the data, grouping is a very trivial task. Then when you have intersection, meaning joining two tables, table A and table B, when you try to join the two tables together, that means that's also is a sorting problem. And how is it a sorting problem? The way you join two sets is you take a table, sort it on the column on which we want to join it with another. You take another table, second table, you sort it on the column on which we are trying to join, and then we go linearly on both the records, and then you go linearly on both the records, and and keep on matching it. So that's far quicker, and that's how most of the join works in case of the databases. Similarly, order by is blatantly a sorting problem. So therefore sorting problem is backbone of processing. Okay, so also whenever we talk about processing, processing always have become a sort of an alias to sorting algorithms. Okay, and every year a new sorting algorithm comes up, or an enhancement keeps on coming up every year. All right, so therefore sorting algorithm has become such an important aspect that there are competitions such as sorting benchmarks where all these companies compete all the time. Okay, where all these companies compete all the time. Like for example, Google won the sorting benchmark on 8th of September 2011 using their MapReduce framework, where they were able to sort 10 petabyte of data using 8,000 computers in 6.5 hours. Okay, last year it is the Apache Spark which has won the complete sorting benchmark uh, by the numbers. Okay, but the most significant work in case of sorting benchmark was by Google, and this one was the very big landmark in the whole sorting history so far. All right, and thanks to the MapReduce framework. All right, coming to the computation. So before we get into the computation, let's see how it happens in case of MapReduce. Or you can say it is a Hadoop MapReduce engine. So here we are going to confuse a little bit. So this is Hadoop 1.0, where MapReduce engine was equivalent of a computation engine. Okay, so this is the computation engine. So the way we had admin node and data nodes, admin node did not do the actual work while it supervised. We had data node which did the actual work. The similar way we have job trackers and task trackers. What did job trackers do? Job trackers basically made sure that, like a supervisor, delegated the work to task trackers. So user comes in, user gives work to job tracker gives work to task trackers, and once all the task trackers finish the work, it returns the results to the users. Okay? So this is a very simplified way. So whatever work you are giving to job tracker is getting delegated to multiple task trackers, and those task trackers are working on it and returning the result. The other way, you can also look at it this way. Alright? So the clients come to job tracker and assign the work, and then job tracker delegates the work to multiple task trackers, and those task trackers finish the tasks and give back the results. Alright? This is another way of looking at it. So a user comes and first it puts the data into the file HDFS. Then the user submits the work to the client. The client creates something called splits, meaning over on top of each block of the data which we have kept in the HDFS. It creates something called split, and on top of each split we give the work to job tracker. Now here we have added one more detail as compared to the previous one. Here we have just told that job tracker will delegate the work to task trackers, right? Here there are little more details. Yeah. Yeah, I can hear you. Uh. Okay. Yes, yes, please. I'll go over. Somehow this did not show me that there are so many comments. Alright, I just had a look at it. Alright, so is the voice clear now? Alright, so I start from the. So should I start from previous or this one? Alright, no worries. Now going back. Alright, no worries. So let me just go over this. It's important we understand this. Alright, so here there is a very simple concept that we have described, that job tracker is the one who receives the request from customer or the user, and job tracker delegates the work to multiple task trackers, and those multiple task trackers get the work done, and then once all the job trackers finish, then job tracker once all the job trackers finish sorry once all the task trackers finish, then job tracker responds to the user. Okay, job tracker takes care of the full job while task trackers take care of only their specialized work. Okay, so so you so basically first step is to understand is that there is something called job tracker who does nothing but does the supervisory role like a supervisor of any job shop floor, where uh, the the job tracker needs to do couple of more things. First, in case one task tracker goes down, it it gives the same work to another task tracker. Okay, and the whatever work was done was done by previous task tracker. All of it is generally ignored. Sometimes it is reused, but most of the time the previous task tracker which died or which became unresponsive after some time, that same work is given to another task tracker. And unless all the task trackers finish their work, job tracker does not respond to the user. Okay. All right. Now the next question from Abhishek is, are these task trackers located on different machines? Yes. So just like we had data nodes and admin nodes, so all of these four things, data node, admin node, task tracker, job tracker, all of these are Unix processes. Okay, these are running on a particular port. As we saw earlier that the when we were looking at the three node on which the data was replicated, there was something called 50010. That is the port on which the data node runs. All right. Similarly, task tracker also run on a similar port, and job tracker also runs on a similar port. Okay. Generally, task trackers and data nodes are run on the same machines. Okay. And we'll see it quickly why. So first is this job tracker delegates the work to multiple task trackers and also makes sure the resilience. Now question arises that how does it delegate the work to multiple task trackers? The way it delegates the work to multiple task trackers is by by basically whenever we are assigning the task to the job tracker, we also tell the job tracker that, hey, what we want is we want to process this particular file, and this particular file is already there in HDFS. So other than giving the work to the job tracker, we are supplying one more information to the job tracker that we want to process this particular file in HDFS. Now based on that particular file, so this particular file would be located on multiple machines, right? So based on this particular file, the job tracker would find out the location of all the blocks in the network. So you are processing a file which has got three blocks. These three blocks have replications across the network. Now job tracker's duty is to find the best three nodes which are free. And only those three nodes will be assigned the work. Okay. Also, you can tell job tracker then please ignore the file and create these many task trackers. That is also possible, but the easiest way is we tell the task tracker, here is my program that you need to execute, and here this is the particular HDFS file that you need to run my program near to. Okay, and that way the job tracker will send work to only those nodes where the file is located. All right. Now that gives a huge benefit to Hadoop, because our data, our big file was anyway located on multiple machines, right? That means that means that it does not have to transfer the data. So our data transport problem is solved. Our work is delegated to multiple machines. Also, it also gave us a huge resilience, meaning if one task tracker goes down, job tracker can quickly find which other node has the same data as the task tracker which has just gone down, and then it sends the work to that particular task tracker and get your task done. All right. So okay, this is another visualization of same thing. So user copies the file to the file system HDFS, or you can assume that whatever data you want to churn, it's already there in HDFS. Okay. Now the user submits the job to the Hadoop client. Hadoop client is the library which does most of this delegation. So Hadoop, the command which we just quickly executed, Hadoop fs something, that is the client. That is the client which we are calling here. So the user, which is you, first have put the file in the file system. Second is it submits the job to the Hadoop client saying here is my file and here is my program that you need to execute, and the client goes to the HDFS, finds out where all this file is located, which all nodes is it located, and creates something called input splits. We'll talk about input splits later. You can think of splits equivalent to your blocks right now. So it finds out all the blocks and then it submits the job to the job tracker. Okay. Okay. So I'll answer your question, Lingli, in a minute. All right. Now the client submits the job to the job tracker, the client as in Hadoop client library, the command line, and job tracker finds out the data from the HDFS, and then it starts delegating the work to various task trackers. Okay. Let's ignore the MapReduce part for now. So it creates something called a job queue. A job queue is something like this particular work was delegated to this machine, this particular work was delegated to this machine, and so on. This is the job queue. As and when the response is coming from each task tracker, the job queue is being updated. The moment all the slots in the job queue are completed, then the job tracker gives the response back to the user saying, here is your result. Okay. So right now the processing which we have so far talked about is in very abstract terms. We are assuming that there is some program that is to be executed. Okay. So here we talked about three things. First, job tracker takes care of delegating the task such that the data is closer to the processing. Okay, it tries its best to execute your code on the same machine that contains the block of your file. Okay, so if your file has got 512 MB, so anybody, so if your file is of 512 MB, how many task trackers? Correct. So for each block, there'll be it will find out which all blocks are located where, and so the selection of those four nodes will be out of how many nodes? Four nodes will be selected amongst how many? Each of these four nodes will be selected from each block will be on how many machines? Three, right? Good. Each block will be on three machines, and which means to select a task tracker, job tracker has three options. Okay, or in case none of these three machines which contain a block or its copies, if none of the three machines are free, okay, So the question here is, so when let's say you have got a 512 MB file. A 512 MB file has got how many blocks? 4 blocks, correct? 128 MB each, which means when the job tracker is assigning the work, it will try its best to send your work to the task trackers containing the data. Now, your data, these 4 blocks, generally would be on 4 different machines. They could be on the same machine. All 4 blocks could be on the same machines also. Alright? That means in the best case scenario, your 4 blocks might be on 4 different machines, and each block's copy would be on there'll be 3 copies of each block. That means total number of for each block there'll be an option of 3 nodes, because all 3 nodes contain that particular data. And in case all the nodes containing a particular block, particular part of the file, if all of those nodes are busy doing something else, then Hadoop might choose to execute the code near to the machine which contains data. So not necessarily it has to execute the work on the same machine, but it tries its best to execute on the same machine. All right. So we'll talk about the this is called data locality optimization, how to configure it. Okay, we'll talk about it at a later point of time. But important part is that okay, so this is another extension of the same here. So job tracker assigned work to H1, H2, H3 and H4. These are multiple task trackers. Yeah, Seth's question is, then there may be one task tracker for 512 MB file if there is on the same machines. So not really. It will still track it as if there are 2 separate tasks running on the same machines. There will be 2 tasks run at the same machine, one for each blocks. Okay. Not 2 as in 4 basically, if there are 4 blocks. Now, Basant's question is, if the duplicated file in the block somehow gets corrupted, how is that handled while the client is trying to read the data? I mean, the data in 1, 2 replica is same and third replica is different. Okay, so the way it is done, again the voice is breaking. Oh, wow. So, what is wrong? Just give me a minute, let me just check. So, alright, my out of 2 connections, one is down. Alright. Yeah. I'm actually worried about if it happens in between, that's why. Okay. So during the break, I might want to restart the router. Alright. So I'll do that. Okay. Now coming back. Now let me repeat the question I was reading that time. So Basant's question is, if one of the blocks, so we talked about that there is the file is broken down into blocks and each block is copied. What if one of the copies get corrupted in between? So HDFS basically tries to keep the something called hashing. It keeps the signature also and does our usual CRC checks. We call them redundancy checks. Okay, and that's a part of a protocol with probably every system wherever there is a communication. We always ensure that with a code, we we generate a CRC code for the whole data and then check whether the data which we have read is having the same signature as the one which was promised. Okay, so those kind of things are very well done, and in case one block is found corrupted, that block is dropped and replication starts. Okay, so so it's based on signature which SDFS maintains for each file or each block, and then based on that, it ensures that whether a file is corrupt or not. Okay, so all right, good question. Now coming back to what we were discussing, so there was a job that needs to be done, and it was found that it needs to be done on four machines because it has its blocks were distributed on four different machines. Its block were stored on four different machines or four different data nodes. Now, what did job tracker do? Job tracker asked name node that, hey, can you tell me where all these blocks are located? It tells us that, okay, these are the nodes containing the blocks. Now you do whatever you want. Now job tracker finds out that which are the task trackers located very near to those data nodes. Okay, which are based on the topology, based on, because it has both the information. It knows the IP address of all the data nodes. Now it also knows that the IP address of all the task trackers. So first it will try to find out same machine, same IP address on which data node is found, and it also checks with its own accounting that this was the work last time we had given and it's still running on this particular machine, so let's not give the work to this machine and let's give the work to some other machine. So this way, it doing that kind of a basic accounting, basic resource management, it gives the work to multiple machines. Alright, so the sound is breaking again. Alright, so stay connected. I'm going to restart my router, so it might take close to 3 to 4 minutes. All right. Hi. So you can hear me? Hi. So can you hear me now? So I'm just hoping that there are no more breaking voice. All right. So getting back to what where we left the discussion. So job tracker finds out the task tracker. These are the task tracker we need to delegate the work to, and afterwards assigns them the task and maintains a queue that this work, the result of this particular task tracker is going to come in this slot, and the moment all the slots are filled, that means all the task trackers have finished their work, and then we will respond to the user giving the job queues, uh, giving the outcome of the all four task trackers. Now, okay. So now, and this diagram basically shows the similar thing on the and shows that data local if possible. Okay. All right. And the other important thing to I was planning was that in case one of the task tracker stops responding, okay, then it will stop sending the heartbeat. What does it mean by heartbeat? Heartbeat means every time job tracker keeps on asking the task tracker, are you doing okay? And task tracker keeps on informing job tracker that I'm doing good. I'm doing good. All right, I need to mute you. Okay. So every time that happens, then task tracker keeps on informing that I'm doing good. In case one of the node fails to respond to the heartbeats, job tracker assumes that particular node to be dead and finds another node to do the job. It finds another node to do the job for us. Okay? Alright, so you can hear me? Any questions at this point? Yes, the job queue is to get the updates from task tracker. That's correct. That's correct. Any other questions at this point? All right. Okay, so here what we have described is the general resource management thing and the selection of the task tracker and the general execution of thing. Now you might ask that in what kind of format. Yes, job tracker will decide what to do with the stopped task tracker. In case task tracker stops responding, the only thing job tracker do is gives the work to somebody else. So heartbeat check is all of this, the whole process, the task tracker, job tracker, everything is a part of our Hadoop component. And now these are part of Yarn, but earlier they used to be part of MapReduce. Can it create task trackers on the fly? Yes. So, okay. So I think I'm understanding it wrong way. Anirudh's question is that can it create task tracker on the fly? So let me tell you what I understood. Let's say there were four task trackers we started with. In case all those four task trackers are not available for the work, can job tracker start one more node having the task tracker process? That is probably the question of Anirudh. We call it auto scaling. It's a good question. So this is called auto scaling. In case all the machines are busy, then we create one more service, turn on one more machine, and delegate work to that particular machine. Now that is not by default the behavior of job tracker, but people have worked on these kind of problems, and the Qbol, for example, and there are few more companies who offer a service on top of the Hadoop, where they have done these kind of enhancements of auto scaling on your network. All right, there are few companies which do that. All right, but it's not generally needed. The way a Hadoop cluster works is that we install job trackers on all the machines in our network, and sorry, not job tracker, we install the task trackers on all the machines on our network. Similarly, we install data nodes on all the machines. We do not leave even a single machine for data node, and that way all our machines are anyway busy. So again, the question from Abhishek is, what is the criteria to reassign the task tracker? The criteria, the primary criteria is, first, it should be very closer to the data we are trying to process. It should be closer to the block which it has delegated the task tracker to. So the task tracker which has been designated to process a particular block should be very closer, very closer to the very closer to the data. All right. The closest the better. Closest means on the same computer first, that is the first priority, or on the same local network, or in the another data center. Now, next question is from Vikas. Number of task trackers created by job tracker is anytime based on the input file size. That is correct, Vikas. That is correct. So if your file size is bigger, that means there are going to be more blocks, and chances are these blocks are going to be distributed across the network, and therefore multiple machines involved in one task. Now, question from Aruna is job tracker installed on all admin nodes? So there is only one admin node, and it's not generally required to put job tracker on the admin node. Okay, we generally dedicate a full machine to admin node. Okay, because it consumes a lot of RAM. It consumes a lot of RAM. Just a second, I'm getting a static from somewhere. All right, so there is only one admin node. So we generally prefer to run job tracker and admin node on different machines. Reason being, job tracker is a little bit more involved, but job tracker is, whenever we are installing job tracker, or whenever we are launching our job, we mention that this is our name node address. This is the address, this is the IP address of our name node or admin node, and job tracker will go there and talk to that admin node, get the file information, get all the block information, and then find out all the data nodes containing those blocks, and afterwards find out all the task trackers near to those uh, data nodes, and then get the execution done. Now, Seth's question is, separate task tracker is created to read each block of the file even on the same machine. That is correct. And we will get into the details a little bit more when we talk further. Okay. So, separate task tracker, not task trackers are created. Task trackers is only single. Okay. Each machine only has one task tracker. We generally have, as a general practice, we create one task tracker per machine. Okay, because there is no point in having multiple task trackers on the same machine. It's like running overloading unnecessarily, because if one task tracker can do the same thing, we don't need multiple task trackers. Okay, we generally do not have multiple task trackers on one machine. Okay, but there could be multiple blocks on one machine, so we can tell task tracker to create multiple tasks, okay, to churn those blocks. We'll talk about tasks further when we go into a little bit more detail. So no worries. Any other question at this point? All right. No questions? Good. All right. Now, so so the work which we were giving so far, we said we will give some program to 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 job tracker to get it executed. All right. In We will give some work to job tracker to get executed, and what form of that work would be? That work will be in the form of maps and reduces. You will create a function called map, you will create a function called reduce, and you bundle it in your program and give it to Hadoop, give it to the job tracker, and tell job tracker to get it executed somehow. Okay, this is part of the MapReduce framework. So we talked about that while giving a job, giving a work to the job tracker, we give the file name and a logic. And the logic here is in the form of two functions. One is called map, other is called reduce. Okay, and how does it work? All right, so let me reintroduce the work. So So we talked about just now, we talked about job tracker and task tracker. So job tracker does something distributedly, distributes the work to multiple machines. Now that work definition should be in what form? That work definition is in the form of map function and reduce function, and that's what is a part of map reduce framework. Okay, so you as a user give out your map function and reduce function to uh, to the map reduce framework, which is nothing but on the top of the job tracker, task tracker, all of this. So we give out our work in the form of map function and reduce function to Hadoop, and that basically this map reduce framework, it takes care of executing your map and reduce on job tracker, task tracker, and get the work done. Okay, so how will it happen? So you will so before executing your work, you give a file on which you want to do something. You will give out your map function and you will give out reduce function. Now once you understand what is going to happen with your map function, you will understand what you need to write inside map function. Alright, so that's a map reduce framework. Map reduce framework takes map function and reduce function from you, and also a file which you want to churn, which you want to process, and then get your maps and reduces executed on the network to get your work done. Okay, so inside your MapReduce framework, you basically write, you basically process the data, and alright, so I think I need to take a step back. So alright, so let's take a 10 minutes break. I'll come back and then we'll discuss in detail. And okay, so 10 minutes break. All right, so should we start now? Okay. All right. So it's okay to ask a question and don't be shy in asking questions in public. All right. So anyway, I'll anyway copy it to all. So we have a question from Ramesh. The question is, does every data node have to be on a separate machine, or it can be so that one machine can have more than one node? So theoretically, yes. Theoretically, yes, you can have multiple data nodes on one machine, meaning multiple data node processes running on the same machine on different ports. As I told you that every data node is nothing but a network process, which means it runs on a particular port. It listens on a particular port. Just like if you run a web server, it listens on 80 port. If you run a if you run a database server, say MySQL, it listens on 3306 port. And if you are connecting to our cloud labs over SSH, it's running on 22 port. Our SSH daemon or SSH service, which is running on all the nodes, is running on 22 port to which you connect to. Alright? So basically, you can run data nodes on multiple ports, okay? And theoretically you can run, but practically there is no benefit, there is no added advantage of running multiple data node on a single machine, okay? Whatever multiple data nodes on a single machine can do, a single data node can also do the same thing. Make sense to you, Ramesh? All right. Alright, so I think a better idea would be that we discuss the MapReduce in a usual manner. For time being, you can think of that. I'll just go through this quickly. In case you do not understand, do not worry too much. We will discuss it again. Alright, so we talked about some execution on the multiple task trackers and those kind of things, right? So the way it happens is when you ask a database to get something done, you give a SQL query, right? You give a SQL query and get that thing done on the database side. In the similar fashion, if you want to get something done from the MapReduce framework, you give two functions. Two functions, as in the functions are written in Java, and you write those functions, and you can actually write those functions in any other language also. We'll show you that. One is called map, other is called reduce. The duty of your map function is you have to give out key and values, and whatever key and values are given out by your map function, the data given out by your map function is collected together and sorted by the key which you have defined. And once the data is sorted, for each key all the values are brought together and send the then for each of the key your reduce function is executed. Okay, so you can think of let's just forget the key value again. uh, you can think of that whatever is there in your map logic, it is executed on each individual task trackers. Okay, and once the work of your map function finishes, the output of map function is sorted and gathered together, and then the work is given to another task tracker on which your reduce is going to work. Okay, so there are four task trackers involved, three task trackers for execution of your map function, and then the data is gathered together, the output of your map is gathered together, and then reduce function is executed, and then output of this map reduce is saved onto the disk. So MapReduce used to be the only way of getting your work done from Hadoop. Okay, but now the paradigm has changed. Earlier, MapReduce and Job Tracker Task Tracker were a single component. Now they are two different components. Okay, so that's a very quick and dirty overview of MapReduce. Now, Amish's question is, do we have to provide sorting function to the input here? So, we do not provide a sorting function, we provide a key on which the data need to be sorted. Okay, a string, a value on which the data needs to be sorted. That's the duty of map, saying this is the primary key on which you need to sort my data, and this is my value. Anirudh's question is, map reduce executes on job tracker? No. None of this actual execution of whether maps or reduce actually happens on task tracker. The coordination work is done by job tracker. Okay? Actual execution of any of these things happen on the task tracker. Do not panic in case you did not understand this whole thing. We'll cover it up again. We'll cover in more detail and more sophisticated manner than now. All right, that's why I'm skipping one slide. And okay, so all right, so this is a general way. Now, in Hadoop 1, this map reduce whatever is there, the way we were getting our work done, the paradigm, and the actual job tracker, task tracker were a single component. But in Hadoop 2.0, which is Yarn, the MapReduce framework is broken into two parts. One, in which we give our program and MapReduce, we give our maps and reduces the logic, and then it gets executed on multiple machines. So the actual execution, the job tracker and task tracker became the part of Yarn, and MapReduce became an independent work. Similar to MapReduce, there are other processing units which can utilize job tracker, task tracker. Earlier, only maps and reduces were only things which we could execute on job tracker, task tracker. Okay, but now, after this MapReduce was broken down into two parts, Yarn took care of executing anything. Not only MapReduce, but it could execute anything. And that has been a really wonderful thing that could happen to Hadoop. Otherwise, it could have basically become very obsolete very quickly. Okay? So now, because of this breaking down, the job tracker, task tracker kind of things became part of Yarn, and whether MapReduce or Apache Spark or HBase or Tej or Giraffe, all of these components can utilize the task tracker job trackers to get their work done, not only MapReduce. Earlier, users were forced to convert their logic into maps and reduces, and only then they could utilize their cluster. Only then they could utilize Hadoop. Now, after Hadoop 2.0, this is what it is. And good news is that as of today, almost every installations of Hadoop is Hadoop 2.0, which is Yarn. All right. So okay. So now this the change from Hadoop 1.0. In Hadoop 1.0, MapReduce and Job Tracker, Task Tracker were a single component, which means the only way we could get our work done by the way of writing our program in the form of maps and reduces, and therefore it was too limited, and hence Yarn was created. And it basically provided the workloads other than MapReduce. It provided the scalability. It provided also what the cleverness of Yarn was, that it was done in a way that you do not have to rewrite your MapReduce program. Old MapReduce will anyway work the way they were. Okay. Now, Amish's question is how much work to convert from 1.0 to. So the definition of your MapReduce function were exactly same. You did not require much of the work to convert it. All right. You just need to recompile your code, and that's all. You just have to recompile the code and then push it again. All right. Now, Now, because of this change, these newer paradigm, so MapReduce is more like a paradigm of computation. Just like SQL is one paradigm of computation, that we form our logic in the form of SQL query, or in our, say, other languages. Say, how should I describe? So in case of Unix, the paradigm is in a form of filters. In the in our usual procedural programming language, the paradigm is very different. We have loops and we have functions. But in case of our SQL, it's the simple query language which we provide. And in case of MapReduce paradigm, we provide our logic in two parts called maps and reduce, and then it has got its own syntax. Okay, we'll show you that. In map and reduce, we basically write our Java program or any other programming language. Now, the other difference when it was made more modular, more generic. So the task tracker was broken down into multiple things. Task tracker and job tracker have become something called job tracker has become global resource manager, and task tracker has become the something called node manager. Those That is one renaming, and these two more components have been added. These three more components have been added so that any logic, not only MapReduce, can be executed on Yarn. Okay, so while job tracker has become resource manager, that's the renaming that has happened, and task tracker has become node manager in Hadoop 2.0. These few more components have been added so that any code can be executed inside Yarn, not only MapReduce, but any code. If you want to implement your own framework and you think that yours may be better than MapReduce, you can create that one without making any change in Yarn, and that is how it basically adds a lot of value. The Yarn adds a lot of value. Okay, so all right, this diagram shows a little more complication. So the job tracker has become the resource manager. User asks the resource manager, hey, I want to execute my program, and this is my the full definition of the product. Okay, and then resource manager talk to each node manager and then tell the work to be done. In the meantime, it spawns something called app master and container. App master and container basically uh, coordinate with each other so that things like MapReduce, things like Apache Spark, all of these will go into each container and start executing, while Node Manager will be used to do the actual execution of the computation, while Application Master and Container is like a small virtual machine you can think of. Okay, so basically these are framework components, and what you need to understand is node manager is equivalent to your task tracker, and resource manager is equivalent to your job tracker in the new form. And you can also see on our interface here, is node status similar to heartbeat? Yeah. So, so yes, that's correct. Node status is similar to heartbeat, and there are multiple heartbeats that are going. So resource manager have to take care of each of these systems. Okay, whether my MapReduce framework is running or not, whether Spark is running or not, whether Spark's code is being executed on Node Manager, or whether MapReduce's code is being executed on Node Manager. So all of these things Resource Manager takes into account. So you can see that as part of MapReduce 2, you have multiple clients installed, and as part of yarn you have resource manager and node managers. Right now one of the node managers have been shut down, so we can have a look at what has been shut down. So you can see that it says that following components are down. We can go to this one, and it shows that only node manager is down. So one of the task trackers is down. It does not impact our computing. All right. Can you please repeat what container and app master do? Okay. So app master and container basically, so for each kind of applications, whether MapReduce or whether Apache Spark, whether Thales or any other form of computation. So MapReduce is nothing but a form of computation, right? Similarly, there are Thales which executes your SQL queries using Thales engine. So for each of these, there'll be one application master. For MapReduce, there'll be application master for MapReduce, and then there'll be an application master called Thales, and all of these will be running in conjunction with container. Okay, container will ensure that each of these application masters do not cross their boundaries, and whatever they require, the application master, whatever they require, they get that data. Okay, so actual execution, actual data intensive work is still done by node manager, and actual resource management is done always by the resource manager, while application specific customizations, application specific the intermediate layers are being done by app master and the container. All right, does it make sense to you, Vikas? Great. All right, so that was a very quick overview of yarn and job tracker, task trackers, and we will go into more details of MapReduce, okay, after this discussion. All right, so a quick cluster hands-on. First, let's have a look at Ambari. Ambari is our web interface, and we are using Ambari as our provisioning tool. Using Ambari, we have installed our whole cluster, and that is probably the easiest way to do. And since we are using hot and work installation right now, in case you are using Cloudera installation, you will be using Cloudera Manager. Okay. So Ambari gives us ability to administer our cluster. You can see that these are all the services running, and these are the hosts. We have how many hosts are there? Okay, clear filter. So we have 4 hosts right now. Okay, and it shows that whatever is up and down. In case you want to add more hosts, you can add more hosts. Okay, all you need to provide is the login password of the machine, and in the form of a private key, and then it will install all the processes that you want to install on the particular machine. Whether you want to install data node, you want to install name node, you want to install something else, it will ask you here in the third step, assign slaves and client, and then it will install those uh, nodes on those. Okay. Similarly, in case you want to stop a service and move a service to another machine, you can do that. Okay, from here. Okay, right now these are the services that are running on Hadoop 1. In case we want to stop something, we can do that. Also, in say resource manager, we can stop it and then move it. You see that? We can move a resource manager in case a machine is overloaded. We can move a resource manager to some other machine. Okay? Resource manager again is something called job tracker we studied. And we have similarly data node. Data node we can decommission also and then add more data nodes. All right. So we can add region server, more node manager. Node manager is what I mean, something which is equivalent of task tracker. Again, going back here. Now these are the services that are running, and this is the status of service, overall available memory on the cluster, and everything. Alright, so that is the quick view of Ambari. Region server is a part of HBase. HBase is a database on top of Hadoop. Okay, we'll talk about those in session number 7. Alright, now Hue is a web interface to basically do various operations. So you can basically create your own folder. Make sure you create your own folder here and then upload a file. So I have already created a folder, so I can go into my folder after searching in this. Alright, and under this I can upload a file. Alright, so directly from my laptop I'm able to upload the file there. Alright, so next is connecting from the I have already shown you how to connect, and overview is, so again the Ambari, in case you did not notice, Hue is running on 8000 port, Ambari is running on 8080 port. Okay, using Hue you can interact with various services. Like here we can see what's going on with Hive and Pig. You will understand what do we mean by those as we go forward. Now on Windows you will have to download Putty and install it and then connect to our server, and there is a installation guide over there. On Unix and Mac you can directly use this. Okay, and you might need WinCP command to copy the file from your local machine onto this, onto Hadoop 1 dot Hadoop 1 dot no big data. Hadoop 1 dot no big data means this Linux machine we are talking about. Okay, so also create one folder here, over here. This is not HDFS. This is our Hadoop 1. Okay, this is our Hadoop 1.nobigdata.com. There is Hadoop 2, Hadoop 3, Hadoop 4. You can utilize any of those. And make sure that whatever you do, you create your local folder. We call it local folder. It's not in HDFS. Okay? You create your own local folder here in which you put your data. Alright? Now, what we can do is from our local file, we can copy from local file using this Hadoop fs command. One way of copying the data was using the Hue, using upload method, where you can directly copy from your laptop to HDFS. If you want to copy some data from your machine, Hadoop 1 machine, you can utilize Hadoop fs minus copy from local, and you give a file name, let's say let's say ratings.csv, or yeah, ratings.csv, and you can copy this particular CSV file onto your folder in the HDFS. I have created a asgiri folder in HDFS. You can copy from here. Okay, it says the file already exists, so I can give it a different name, ratings duplicate.csv. Alright, so I would have to mute you. Alright, so it has copied this local file into this place. Now I can have a look at this. So here this is my folder, and I can say not this, I'll have to say ratings. So you can see that this file has come here. Okay. So this way you can copy the data from local machine to HDFS. This local machine means Hadoop 1 or Hadoop 2 or Hadoop 3, wherever you have SSH. Okay. Now your question would be that your data is on your local machine, on your laptop. How you take this data to Hadoop, right? That will be your question. So there are two ways. One is directly use the browser. Using the browser, you can upload a really decent amount of data in today's time. But in case you don't want to use the browser using Hue, if you don't want to use it, you will have to do it in two steps. First, you will have to copy the data from your local machine to Hadoop 1.no big data. And in the second one, you will have to move that data from Hadoop 1 to HDFS. Okay? You'll have to say Hadoop fs minus move from local and the file name and to the folder. Okay? Alright, so that is copying of the data. Also, the file which we have just copied, we can check where is it located actually. Okay, on which blocks it is located. Okay, just for curiosity, although it adds no value. So it shows that okay, I'll have to give absolute path. Absolute path means starting with the slash and slash user slash student slash asgiri, and so this file again, it is slash user, not users. Alright, so what am I trying to show you is where is this particular file located, and again in the same format you can see that the file is located here. Okay, there are no corrupt blocks, as you can see. There are no missing replicas, and here okay, it says the replication factor is 3. Then why doesn't it show the locations? Okay, okay, it's a little above. Yeah, here it is. Okay, so alright, I think we are missing something in the command. Yeah, files. There is one more option called files. We need to mention that. Minus files. Alright, now you can see that. Now you'll see this here. These are the various machines containing the data. Alright. Okay, so yeah, till here. Also, you can change the replication factor of your file. Okay, you can change the replication factor of your file this way, and then you will be able to okay. So here I'm setting my replication factor to 4, and then again I'm checking what's happening to my data. So it shows that the okay, so here you can see this. Okay, now it has copied. It says that target replica is 4 but found only 3 replicas. That means it is in the process of copying it. Okay, now it has copied it. Now you can see average block replication is 4. Now what does it mean by average block? For each block, how many replications have happened, and then it computes it and divides by total number of blocks. That is average block replication. Okay. Thank you, Sandhya. All right. Also, you can bring the replication down again to maybe 2 or 3, whatever you want. Okay. Also, those who were asking me the question about your HDFS, here, since I am logged in as admin, I can control the various configuration of HDFS. I can tell that name node has to be this much, and also I can tell that here this is my not this one. So here the default replication is 3, that's what I have set. And if I set it to 2, by default my default replication factor will be 2. And where is my... So these are the various settings that control my HDFS. Now block size here. This is my block size. Okay, so this is the block size. Alright, so Amish's question is that when you change a Java parameter, when we are changing any of these parameters, does it take place after finishing the jobs if they are going on? Yes. It makes sure that it changes only after the work is done. Now Anirudh's question is, when you say the default replication is 3, you may also need IP address where replication needs to be done. So yes, so that anyway is already configured. Okay, name node knows where are the data nodes. Okay, name node knows all the data nodes, and it knows all the details. Okay. I could actually show you the config file. So name node knows all of that already. All right. Did I understand question correctly, Anirudh? All right. So good. We were able to create a file, copy a file to HDFS from command line, and we were also change its replication factor. All right. Now this is just a classic running a MapReduce job, just to give you a flavor of what's going on, although it has nothing to do with. So Seth's question is, can replication factors value can be more than available node? Why don't we give it a try? The thing is, we can set the replication factor to whatever we want, but Hadoop will deny. Hadoop will say that your blocks are under replicated. If we say 10 here, or say 5, right? And we have total number of 4 data nodes. Now when we do that, it will not give an error right away, because in future if you add more nodes, then it will create the replication factor. But here it says that target replica factor is 5 but found only 2 replicas. Now after some time it will say target replica is 5 but only found 4 replicas so far. Okay, so it's basically copying the data. It's basically in the process of copying the data, and it might take a little bit more time. And it clearly says that your blocks are under replicated. All right. Now you can see target replicas 5. Now it has copied, made 3 replicas on these nodes, and after some time it will create 4 replicas, but it cannot go beyond that. All right. Okay, I'm bringing it down to 2 again. Alright, so that's what it is, and you can also execute and MapReduce job using command line in the way Hadoop jar and a jar file, and then you can execute it. Alright, now that's how you will execute, this is how you will execute a MapReduce job, and let's just execute something. So it says Hadoop jar and we give a jar file. Jar file is like a zip file in which we put all our code together, and then we give all the arguments to our job and get it executed. Right now it's giving an error saying the particular folder, output folder, already exists. So if you have already if you already have you know, output folder, it will give an error. Alright, so this is the way a map reduce process runs. Now from here you can take few things. First, it takes time to run map reduce. You can see that it has given us a URL to track the progress. We have asked Hadoop to do our job of some word count. It's doing it slowly at its own pace, but it's getting it done on multiple machines. Alright, and this is where it gives us the progress, and once it finishes the work, it will put in the HDFS folder. Alright, so now let's begin with our very important exercise called thinking in MapReduce. Okay. Alright, so in this exercise, you all have to be involved when I ask questions. Alright, so a very simple problem to all of you is, if you have a plain text file of all of the Lord of the Rings books, how would you find frequencies of words? Yes? Anyone? Okay. So Vikas will go to Mapper Reducer after some time. Okay. And we will try to understand the usual approach. If your boss asks you the same question, get me the frequencies of these words which are available in this particular folder, what will you do? Any approach will be fine. Mm-hmm. Okay, okay. I'm getting a very brilliant answers, and let me just copy paste them here so that I can correlate. All right, all right. So I say colon slash n with simply colon, and let me just sort it. So Abhishek says using a hash map for every word, calculate the frequency. All right. Let all of you finish, then I can. And all right. So all right. Yes, Ingoba, go ahead. So Abhishek is saying we will create a hash map. Great. For every word, we compute the frequency. Okay. So what you are saying, Abhishek, let me repeat if I understand it correctly. That w probably what you are hinting at is that we go word by word in this file and we create an empty hash map where in a hash map is like a dictionary. In dictionary you have word and the meaning, right? In the same way, hash map contains key and the value, and the hash map you can quickly give the key and get the value. Okay, so what Abhishek is hinting at is that we go through one word by word. So, by the way, is it Abhishek Verma or is it Abhishek Parmar? Okay, it's impossible for me to actually distinguish. Okay, all right. So, all right. So there is no way I can make a distinction. All right. So here, this is one good approach. Okay. So in this we'll discuss this approach immediately after this. Similarly, Anirudh says use wildcard character, Lord of the Rings or pattern match. Okay, and then what will you do, Anirudh? I want to see a little bit more details. Aruna's point is the create and then list of words, order by n group. Great, great, great. Okay, and Dia is saying that per parts. I did not get this one. If you could little bit more, give me a little bit more details. So what we want to do is frequencies of the word in this particular text. I want to see that how many times each word has occurred. Okay. So distinct words from this text and then count. Okay. Now Kirti's point is that do we create a task function with regular expression to find frequencies of words? Okay. All right. So no, my question was to you that how would you do it in a usual manner? Okay. Okay, Ramesh is saying that all you need to do is sort the words alphabetically and then count. Okay, that's good. Lingley's point is the map the word, okay, then process them via reduce count. Okay, so that's moving ahead. Nitin Patel says creating trie of file parts. Okay, this is interesting. So that's a little bit more involving. So because a try will be too intensive if you see, because we are not trying to count the substring of the word, right? We are trying to count the full word. If we were counting the substring of the word, then try could have been a wonderful idea. Okay? So those who do not know try, just do a Google search. It's not a very difficult thing. It's a data structure. And in autocomplete, when you type something and Google autocompletes, those kind of problems we generally use try. All right. Count the occurrences of word on each block and add up the counts. Okay. Count the spaces. Okay. But how do you count the spaces? So we are not, Robert, we are not counting the words, total words. What we are counting is each word has come how many times. Okay. Seth is saying sort using map and then find using reduce. Okay, you are moving ahead. Vikas is saying create a mapper and reducer. Then the other one is create a hash map with key as word and value as count. Good, good. Split the file into chunks with MapReduce function. Okay, we'll discuss the MapReduce later. Use something which can sort and add the existing word and then try to count the sorted word. Good, very good. And Sean is saying search where word equals something. Okay. Sandhya is saying it's essentially a group by. Brilliant. And we need to take all the words based on separator first. Yeah, separator is space or tab here. All right. Correct. So, Seth, that is correct. The slide title is Thinking in MapReduce, and this is the first step. So, without MapReduce, how did you do these kind of things? All right. And then we will go into the details of dynamics of MapReduce, and we'll go further into more details later. All right. So here we have a plain text file, and we want to find out the frequencies of the word in this particular text. All right. Now, just let me say that we want to find out the frequencies of the word in this one. Okay. Whatever we have here, we want to find out the frequencies. And how will I do? I will just, my approach will be replace space with new line. Okay. Now do a sort and then you do a unique minus C. Okay. And again I'll do a sorting again. Now you can see this is my word count. This particular thing has come 17 times. The has come 10 times, and you can see that. All right. So that's my approach, and I would like to see your approaches. Okay. So great. We have got very good answers. And so first one answer is that create a frequency hash table, or we call dictionary, and for each word in the file increase its frequency in the hash table. By default, if a word does not exist in the hash table, we assume its frequency to be 0, and then when there are no more words left in our file, then we print whatever we have accumulated in the dictionary. Is this approach clear to everyone? Great. Now, do you see any problems with this approach? Brilliant. Brilliant. Yes. So Srinivas, if you look at it, we cannot get faster than this actually. Okay? We cannot generally get faster than this. All right. So great. Now there are two problems with this. First problem is that if the file size grows, what we are doing here, whenever we say frequency table, it is going to be loaded into the memory. And if the file size keeps on growing, it will cause the hash table will become bigger. And if hash table becomes bigger than the computer's RAM, then we will no longer be able to stuff more words into the hash table and we will give up. We'll get an error saying memory overflow. So first problem is that. Next problem was too slow. So in a way it is too slow. If we had multiple computers doing the same thing, part of the work, maybe we could make faster. So Srinivas, your point is valid in a way. And Ingo by saying reading time is slow. Yes. If the file is too large, then the time it takes from the same hard disk, it is going to be really high. Okay. Now there are a lot of words, then it is going to be problem. That's correct, Son. Linear approach, that is another problem. So here we are not able to make it parallel approach. While one thread is reading the data from the file system, other thread should be computing the frequencies. Correct? And that is why it's a linear approach. And therefore, while something is finding the frequency of a word in the hash table, other one is waiting for I mean, you are not reading the data from the disk parallelly, so you are not utilizing the CPU properly. That's a Lingley's point. Good, good. Thank you, Sandhya. Yes, it's a serial approach. Dia, thank you. So performance when we have big volume, good. It's not scalable as yes, good. So it's not scalable as hash will not fit into the memory. Brilliant, brilliant. So everybody got that why this particular approach is wrong. But if this data is very small, say if your RAM is 10 GB and your data is 1 gigabyte, then this approach is good. And to read 1 gigabyte file, it is it takes around 5 minutes, 5 seconds of time from the disk. So overall, it will take 5 seconds to finish. Yeah. Thank you, Ngoba. Yes, it's not wrong, but it is not efficient. That's a better way to use, the better words to use. Good. And all right. So now, what other approach did you suggest? So one of the approaches, one has, I think Sandhya or somebody has suggested. I saw that. Okay. So other approach was using group by. Okay. So I think Aruna suggested this approach. So Aruna and Sandhya, I think. Yeah. Yeah. So, all right. So the other way would be, since databases have been handling the data which is bigger than the RAM for quite some time, right? Databases handle the data which is far, far bigger than the RAM. So, in the approach number two, what we are doing is we have figured out that our approach number one suffered from the memory problems. So, we have come up with another solution, which is break all the books into one word per row in a table. We've stuffed the whole all of the words into a database table containing only one column called word. And then we apply group by and then get the results. Okay? So those who are not aware of SQL, SQL provides you a way to group the data quickly. If you present the data as a table, you can apply things like group by. Okay? Just like an Excel sheet, it provides you all kind of operations. Okay? So SQL provides you a way to group by. So Abhishek Parmar, are you able to correlate here? Because I'm not sure if you have uh, been acquainted with SQL. All right, so you're comfortable, great. And so all we did was we broke down one word per row into a table, and then all we did was group by and then count. So do you think this approach is correct? So probably this is the way you will do if your boss asks in the office that can you give me the count of these words in this particular report. Most likely you are going to use this kind of approach. Alright, now there could be a third approach. So who is acquainted with the Unix pipeline? The third approach, what we did was we replaced the way I gave a demonstration to you in the plain text. All I did was first I broke down space or tab into new line such that there is only one word per line. You can see one word per line. Alright. Next thing I did was I sorted it. Okay. I sorted the data, and then all I did was I did unique minus C. And here it has computed the frequencies of the word. Alright, so this is the approach which is being demonstrated here. Cat file means display the file, SED means replace space or tab with a new line, and such that each line contains one word, and then sort it. There is one little argument here. You see the command line parameter or command line argument. What does it say? It says that sort my data but do not consume more than 1 gigabyte at a time. And this sort command is very beautiful in the sense that it will internally break down your file into 1 gigabyte size chunks and then sort each chunk and then combine them together. Okay, that's what sort command does. Okay, so sort command can basically sort hundreds of gigabyte of data using 1 gigabyte of memory or whatever parameter you can configure it with. And then using unique. So Amish's question is that where did 1 gigabyte come? Is it something which no, here I am saying 1 G. You see 1 G? Because my RAM was around 1 gigabyte, so I said only use 1 gigabyte of my computer's RAM. Okay? So I've specifically said here that please use only 1 gigabyte of memory. Because all the algorithms and sorting algorithms you must have studied, they all utilized they all loaded the whole data that needs to be sorted into the memory, right? But this command, what it does, it slices the file into 1 gigabyte size parts and individually sorts them and then merges all those parts. Brilliant. Brilliant. So that was my next question, Abhishek. So what problems do you see with approach number 2, which was SQL, and approach number three, which was using these sort commands, okay, of Unix? So now, all right. So so what are the limitations do you see in approach number 2 and approach number 3? The speed due to RAM. All right. All right. So yeah, keep answering. Yeah. And then I'll read it out one by one. Anybody else? All right, so let me talk about it. Abhishek says that it is the most simple solution. However, it suffers from it suffers from it suffers from the some of the same issues as the first one. It is limited by the capacity of one machine, that is disk space, serial execution, and also the disk read speed. Abhishek, and brilliant. Okay. Now, Sean says that the speed will get hit because of the RAM constraints. Good. Vikas says the approach to complexity is more in inserting each word into the DB, which is going to get hit. That is also correct. But that you can, get around it by inserting sentences and then using the split commands of SQL to basically split the data. All right. Or using the import functions of the SQL databases. All right, but yes, definitely it is a complex. It's a very high load process. Now, Diaz is saying depends on the language. Okay, so what are the problems do you see with approach number 2 and approach number 3, Dia? I want to understand that. Nitin is saying sorting and merging. Okay, so I did not get your point. So you are asking me what is mean by in memory sort one was referring to. All right. Okay. Approach 2, which is SQL, is still sequential. Tables are formed may still have limitations on how database can process brilliant. Also, those who are wondering whether approach 3 can be made parallel or not, it can be made parallel. Okay, it can be made parallel by by using something called split, and also basically you split the file yourself, and then for each part you can execute the sort command separately. Okay, great, great. So we have got almost all the answers I was looking for. So first is the moment data starts going beyond RAM, the time taken starts increasing. As Sean says, that the moment you hit the RAM, the the time taken starts increasing, and the following start becoming the bottleneck. The CPU might become the bottleneck. Okay, the disk speed might become the bottleneck because you are going to read a lot of data. Then disk speed is probably the one which is going to become the bottleneck. After around after around 6 7 GBs, it becomes disk speed becomes the constraint. After around 6 7 GBs, because after around 6 7 GBs means around 30 seconds. Reading 6 GB data from a hard disk takes around 30 seconds. Next becomes the bottleneck. The next bottleneck becomes the disk space. Why? Because for splitting the data, for keeping the temporary location, you're going to consume more space, and therefore the disk space might become the constraint. Okay. Now I'm going to talk about another approach, the fourth approach, which we call as external sort. Okay. In this approach, so in first approach, what we did was we created a dictionary and kept a running count of all the words found so far. And then we did SQL, then we did Unix commands, and now I'm talking about another approach. So in this approach, what we do is on the launcher side. So we create a machine, we take a machine, we get our work done using multiple machines. In the fourth approach, we call it external sort. So what we do is we split the file into we split our input text file into multiple sections, and one section or one part of the file we send to machine 1. Second part of the file we send to machine 2, and let machine 1 and machine 2 use the dictionary or whatever approach they want to use, and let machine 1 and machine 2 give you back the frequencies, and then you combine those frequencies to. All right. Again, the voice is gone. Can you hear me? All right. So what we are trying to do here is we are splitting our file into sections which can be handled by individual machines in reasonable time, and then we are sending the individual parts to each machines, and then getting the frequencies computed in either using whatever techniques which we have used so far, and then we are combining them together. Now your question might be that how do we combine the sorted data? How do we combine the sorted data? Because machine 1 and machine 2 is going to give you the frequency which are supposed to be in a sorted order. Okay, it is mandatory because you can combine, you can merge the sorted data back very easily. Now I'll show you this. Imagine that 1 2 3 4 1 2 3 10 13. This is your, or let's say, let me reduce my headache. 1 13 12 and 1 2 5, right? So these are, so basically each of the machine will give us the sorted data here, machine 1 and machine 2, and then we'll combine them together, because it's far more easier to create a sorted list from two sorted lists. Okay, imagine that we have two sorted lists, one is this, other is this. It's quite easy to combine them by just computing who is smaller in the front. Okay, so who is smaller out of two? Both are equal, so we take both of them out and put it in our output. Now out of these two, who is smaller? 2 is smaller, right? So we put 2, and then we pick 5, and then, yeah, right. So here I am talking about a very simple approach so that we can all understand. But if you have more than two rows to combine, if we have more than two outputs to combine, we would better use a heap. Okay, you can do a little bit of research. How can we merge multiple sorted arrays to form a single sorted array? Okay, so as it just demonstrated that merging two sorted lists were really fast, right? As compared to sorting an unsorted data, or merging unsorted data and then sorting it, merging the sorted data is far more faster. Okay, yes, that's correct, Jahir, thank you. So machine 1 and machine 2, whatever results they gave, launcher will merge them just like that and give the results. Alright, so you can see that SAR array was converted by machine 1 into ray 2 and SAR 1, and machine 2 converted ga ray as ga colon 2 and ray 1. It basically gave the frequencies of the word in the input, and then launcher merged it and gave the output. Do you see any problem in this approach? Before that, I have missed so many comments from you. Alright, yes. In the memory sort I was referring to, that was Nitin Patel. Okay. Oh, this is what you were trying to mention. Oh, thank you. Great. So this batch seems to be pretty smart. All right. And okay, that's the Chuck's approach I was talking about. Okay, I think I missed this approach. All right. And now here, Jahir's point is, can we use BST for faster? I think we will use um, for merging. We generally use a heap. We can go into data structures a little more, but here, all right. Now, okay. So the problem statement is quite simple. That the launcher is asking machine one to do part of the work, and then launcher is merging the results. Do you think there is a problem in this approach? Okay, good, good. Kirti says launcher has to wait for all the machines to finish. Okay, so your statement is partly true, but not entirely true. I'll show you why. So if you have these three results returned by these two machines, so it can basically merge these two by the time the third one is performing the work. Okay, so it can start working as soon as it has two results available. Okay, but it still has to wait for all the things to finish. Okay, Ingoba says that, what if any of the machines fail? Brilliant. What if any of the machines fail? Good. Then Abhishek is saying assigning time. Good. Okay, assigning time, meaning it will take some time to assign. And the other part is launcher has to wait for all the machines to finish. Brilliant. Any other points? Keep them coming, yeah. So my question is, do you see any problem in this? So launcher sent file to machine 1. Machine 1 gave the frequency back to launcher. And these machine 1, machine 2 and the launcher are three different machines connected in the network. Do you see any problem? Bandwidth. Good. All right. Great. So the problem with external sort, as you have said, is okay. So Jahir's point is that we could improve on merging by, can we have some intelligent uh, thing, before we split the file, we might find files take longer than others. Okay, yeah, we can definitely do all those kind of things in order to optimize this process. You can definitely do those optimizations. Correct. Data transfer time to other machines. Brilliant. So I think you all have answered. So there are basically multiple problems with this external sort. First is time consumed in data transport. Launcher will take a lot of time. If we have a terabyte of data to be churned, then it will take a lot of time to transport the data over the network, maybe around 48 hours. Okay? For each requirement, we will have to build a special purpose network program. For example, Ingoba says that it is going to take wait for so it is going to be a problem if one machine fails. Then you have to build a logic. What if one machine fails? We'll give it to some other machine, or we'll retry this thing. So the engineering has to be done. Assigning time will be there, and that is again, assignment will be a engineering problem itself. And similarly, waiting for the machines to finish and all that logic has to be built, and the every time a requirement comes in, we'll have to build a special purpose program catering to all these kind of complex uh, problems, right? And therefore, to avoid all of this, we use MapReduce. Okay? No, it's not over-engineered solution, Nitin. The You will be amazed to know that in 2002 we actually used to use this kind of a solution, and this was considered really brilliant. Okay? When we had at DShaw, we had a lot of nodes, and we were using this kind of approach long back. Okay, we did not invent things like HDFS, and we did not invent things like MapReduce that time. All right. So the solution to these problems is MapReduce. Again, so probably by now you are convinced that MapReduce would be able to solve these problems. So MapReduce basically does things like this, except for transporting the data, except for only working on frequency problem. It can work on multiple problems. And so we will go into the details of MapReduce in the next class, and then we will go with more details. All right. If you want, you can attempt these problems. You can the subjective problems if you wish. If you got the hang of MapReduce, then you can try to at least attempt the first problem. Okay. And then we'll go into the details of these problems on the next. So Abhishek's question is that I'm not sure about the first issue. Time would still get spent in copying over of the file. That is correct. But whenever we deal with a larger data, it is assumed that in an organization, by default, you will keep on copying the data onto HDFS. Okay? So as a general practice, so whenever we are processing the data, mostly the data will be available to you already on HDFS. Okay. So yeah, the assignments are the quiz only. Okay. And if you guys can give me 10 more minutes, then we can discuss basics, and then we can go for. All right. All right, no worries. So finish your assignment. Okay, so we'll discuss the rest of the things on the next session only. All right. Okay. So assignment, you finish the quiz, whatever is there in your course page. Okay. And here you can take the course quiz, finish this one, and also go through the regular expression session if you have not already gone through. Okay. And if you have a little bit more time, go through the subjective questions. Okay. You can go through the subjective questions. All right. So we'll see you on next Saturday. Till then, have a great day. And on this, during the week, please schedule a 30 minutes one-on-one if you need any help in connecting to the cluster, understanding how to use HDFS, how to run commands. For all of that, just just drop us an email at hadoop@nobigdata and give us 3 time slots so that we can schedule a one-on-one. All right? Okay. Thank you, Ling. Uh, all right. I'm happy that you find it useful. All right. Bye bye, Dia. Okay, so in Goba you can follow the follow that you know thing. Okay, so you follow the installation locally on your machine, and then you can. Okay, okay. Could you just give me a screenshot of what error are you getting? In case something serious, we can discuss it over the weekend. All right. Yes, we have definitely a great set of participants, and thank you very much. I am totally having a great time. All right. Bye bye. Have a good day.